If you want to test a machine's intelligence, don't ask it to do calculus. Give it a mundane, everyday story and see what it does. Here is our test scenario. It was a rainy Tuesday morning. Rahul, a hungry second-year CSE student, walked into the campus cafe. He picked up a chicken sandwich from the display counter. He handed 50 rupees to the cashier to pay for it. After finishing his meal, Rahul felt full and happily went to his artificial intelligence class. When a human reads that text, the brain instantly executes several parallel processes. You parse the logic of the rain, map the physical objects like the sandwich, and intuitively fill in the unwritten sequence of chewing and swallowing, all in milliseconds. But a computer lacks that intuitive context. To a machine, those sentences are an unstructured void of character strings. The computer sees letters, not a narrative. To build generalized comprehension, we have to teach the AI to deconstruct this paragraph using a composite of 5 distinct knowledge representation architectures. True artificial understanding relies on translating human syntax into explicit, computable data across multiple structural layers. The first layer we apply is propositional logic. This is our baseline methodology for extracting rigid, true or false facts from the narrative. This diagram maps the text into Boolean variables, P, Q, R, and S. Arranging these into a modus ponens equation establishes a rule: if R, then S. Since the fact R is true, the machine automatically deduces S. This proof handles states perfectly, but is entirely blind to the physical world. It cannot compute what a sandwich is or how to interact with it. Logic establishes absolute truths, but because it fails to define the composition of an object, we need an entirely new structural layer. To solve the object definition gap, we introduce semantic nets. This architecture maps out physical objects and their relational hierarchies. The system uses specific nodes to represent distinct physical objects or people, and directed edges to define exactly how they relate to one another. Look at this directed graph. A Rahul node connects by an is-a edge to CSE student, and a went-to edge to campus cafe. The cafe connects to a counter, and sandwich physically links to chicken with a contains edge. The machine now successfully maps physical containment. It also computes that Rahul inherits all the baseline properties associated with the student node. The AI grasps complex spatial and categorical relationships. However, a static graph cannot efficiently track states that change over time as the story progresses. To manage time and evolving conditions, the AI implements frames. This third layer tracks changing states and stores stereotyped attributes about entities in our story. Frames operate as an object-oriented structure. We create a specific instance for Rahul to monitor his exact parameters throughout the narrative. This matrix represents the frame for student Rahul. As the narrative progresses, the current state updates from hungry to full. The architecture also embeds automated triggers. An if-needed daemon in wallet balance executes a mathematical subtraction of 50 rupees when he pays. With this dynamic table, the machine tracks possession, geographical location, and internal physiological states simultaneously. Frames give the AI an active memory of changing states, yet they do not explain the physical mechanics of how an action is actually performed. To extract pure physical meaning from sentences, we move to conceptual dependency. This layer strips away the ambiguity of human grammar. In English, stating that Rahul handed 50 rupees to the cashier or the cashier took 50 bucks from Rahul are grammatically distinct but physically identical. To resolve this variance, Roger Schenk's methodology replaces ambiguous verbs with standardized primitive acts. This diagram deconstructs payment into CD notation. The verb becomes ATRNs, transfer of possession. The actor is Rahul. The object is 50 rupees. The secondary consumption action undergoes the same process, translating into ingest, with Rahul as actor and sandwich as object. Because these CD structures are absolute, changing the syntactical phrasing of the input text will not alter the final data output. Physical reality remains constant. Conceptual dependency gives the machine a perfect reading of physical mechanics. However, it remains blind to the unstated events occurring between these discrete actions. Look closely at the original text. It never explicitly states that Rahul chewed his food, swallowed it, or even initiated the order. To fill in those blanks, the AI utilizes scripts, a predictive architecture used to map out and sequence unwritten events. This diagram illustrates the cafe visit script. The template triggers because entry conditions are met. The timeline then populates 5 sequential scenes, utilizing CD primitives: entering, grasping, payment, ingestion, and exiting. WeIce generates all the missing intermediate steps, filling in the gaps that human communication inherently leaves completely blank. Scripts provide a structural layer of predictive context. Using these templates, the machine fills in the missing steps of a sequence, replicating the inferential logic humans use to navigate the world. We started with the difficulty of converting unstructured human syntax into usable, computable data. This composite view demonstrates the final model. All 5 architectural frameworks operate simultaneously to analyze a single paragraph of text. Propositional logic and semantic nets act as the bedrock, establishing baseline truths and defining the physical relationships of the objects. Frames and conceptual dependency operate as the active engines, meticulously tracking variable states and parsing the actual mechanics of physical actions. Finally, scripts act as the overarching predictive overlay, allowing the system to logically sequence assumed events. Deep comprehension is not achieved through a single algorithm. It requires the synchronized execution of these distinct frameworks. By systematically layering these techniques, we move past raw syntax to create a comprehensive data model, one that accounts for the logic, objects, and unstated sequences that define our communication.